Hi all, so I'm Stuart Gray. I'm the technical manager for GE Power out of Houston office. So just a quick presentation to show you what the manufacturers are thinking about in terms of arc flash. So a bit of recap into what Paul was saying earlier on what is an arc flash and how we need to deal with it. So it is a high resistance fault. The current can be low, but the main things that as a manufacturer we need to be careful of is the outputs to it. So massive amount of heat, massive amount of pressure, and fast shrapnel. So that's what we've got to design all of our systems around. Also, when we're doing the design, we have to look at, we have a product safety system that we do when we roll out any new product, and it really tries to encompass all of the main failure modes that an equipment could undergo. And so we pull our own metrics on our own failures of our own equipment, and what we see is that the main causes do come down to human error. In the majority of cases, they are people that have opened up a piece of equipment for maintenance, that have dropped something, they have been doing improper live working, etc. And less so on the equipment failure, but we do still see normally in the oil and gas environment loose connections. It's got a high vibrational environment, and insulation failure is very common. So what engineering practices have we got to be able to mitigate this? So arc flash is expressed in I squared T, right? So you've two factors. You have current and you have time. So if we can reduce either, then we're going to reduce the effect of an arc flash. So we can reduce the time by protecting systems. So we spend a lot of time spent in designing and discriminating in protection systems, so we are able to clearly isolate a fault but not remove the operational readiness of the equipment. There's nothing worse in an offshore platform than continued nuisance tripping. So we've got to constantly try to maintain that operational readiness. So protective relay techniques are quite complex in that way. What I'll probably spend more time talking about is non-protective relay techniques. What other things have we got to do that we can protect other than standard protection systems? So offshore, right, the power system is reasonably complex. We have the generations generally on board the vessel. We have a number of contributing loads. So how do we, the level of arc in any of those points is made up from the system fault level and the fault clearance time. So ideally we want to be able to reduce the amount of current that any piece of equipment can be seen at any given time, and we want to set the fault clearance time so as to trip in the fastest time possible. So, but there's some complexities here. So you would expect that if you're on a power system that running one generator, as an example, when you have 6 generators on a vessel, you would expect that running one generator would give you the least amount of fault level current. But in truth, it doesn't always necessarily, and that's where there's this compromise, and the studies that we talked about are really need to take place. In actual fact, if you run one generator and you have a certain impedance fault on a low voltage piece of equipment, for instance, it will take the protection system much longer to see and to clear than it would do if it was being fed in by multiple generators. So in actual case, the net result is worse. So we need to look at all of those systems. The other, which was in reference to my question before, is we also have greater and greater levels of power electronics and hence capacitance in the system. And part of these systems assist the overall power management system on a vessel by being able to, on voltage dips, being able to pump energy back into that generation system. So it's very difficult for a drive manufacturer to be able to determine whether there is a short circuit or whether there's just a need to transmit power. So that's and as such we have a regeneration problem that we need to deal with. So some of the things that we can do, right, is we can add reactors, we can increase the impedance of transformers. There's electrical balances we can put into this plant that will reduce the fault current. We can put faster operating breakers, protection systems. And we can also say in operational guidelines that instead of running a very common closed bus system where we have all the generation in one, you should split that bus and you should keep it running and keep an individual section only being able to feed those individual component parts. So there's multiple things that we can do. There's a bunch of technology as well. There is current limiting fuses, which we spend a lot of time doing and planning into our overall discrimination. So how can we, again, being able to differentiate between the normal load of a system and a fault load of the system. There is electronic current limiters. They work, they're incredibly expensive, they're incredibly big, and they're not really practical, they're not really adopted in most cases. They're only used in really extreme cases. So not really relevant for a manufacturing system. We wouldn't remain competitive if we put this into all of our systems going forward. Arc-resistant switchgear. So this is where I'll probably spend the rest of the talk talking about. Arc-resistant switchgear is where what can we design in our panel, and it's not only switchgear, it's all of our electrical panels. How can we design them to ensure that the arc blast does not hit an operator? And what are all the things we can do around that? Also then last, in terms of non-standard protection systems where we're looking at current, there is optical arc flash protection, which we do supply in many cases, which is just looking for that bright light coming down a busbar chamber, and when it does, we can operate through diodes and we can operate incredibly fast triacs, in fact, that fire the protection system, and we are able to clear faults much more readily. Again, the trade-off is somebody comes into a switchgear and takes a photograph, it sets off the protection system and shuts down your power system. So, we try to design around that, but it's this balance again with operational readiness and against protection systems. So arc containment systems. So offshore, it is required and is in place in every medium voltage system. Only now are we starting to see that move into low voltage systems. The idea is that we will contain the arc within inside the four walls of the piece of equipment, and we will vent it away from where personnel will be. So it needs to be designed from the ground up. It needs to be every nut and bolt needs to be designed in a part of this system to ensure there's no weak points, and then it needs to be exhausted somewhere. So generally in offshore we have quite high panels. So generally you'll exhaust out the top, and then we will do many studies, which I'll come on to and tests to make sure that when that comes up in the switchgear room, that it will not rebound off and come back and kill an operator. That we will have to define very clear clearance spaces for that arc vent to exhaust. So what we do is we design the system, we do an arc flash study as we go, and again, it's very difficult for a manufacturer because we've got to maintain competitive, right? So what do you need to have a really solid arc contained system? You need a lot of space, right? So it's the first thing that we will lose bids for every single day of putting the equipment if we make a system that's bigger and heavier than any of our competitors. So that's a real challenge. You want space for this massive pressure to be able to exhaust. We need all weak points to be fully enforced. So the days of having multiple indication lights on your front door, the days of having plastic vents to bring in normal airflow, they've got to go if we do real arc contained systems. It's got to be reinforced systems. In fact, the doors have really got to be bolted shut. These nice hinges that you can get to open the door, the bottom line is you need that door, you need everything in there to be completely welded shut, and the weak point to only be the chamber at the top, which is going to vent all of these gases. So what we do is we design that system. We then do our worst case fault level system. So what is the biggest amount of fault current that we could ever see on any of the systems that we're designed to? We will certify that panel for that rating, and then we will take it and we will continually blow it up. So we'll take it to a test rig. We use commonly one called IPH in Germany, and where we put various different resistors of shorts on various different points of our equipment. And yes.
You have rigs out there that are over 40 years old.
Yeah.
I mean, obviously they are grandfathered in because they don't have any kind of
That's right.
payment like this.
Yep.
Do they ever upgrade them, or are you looking at just the newer stuff coming out?
So the it's one common place to do a full upgrade to be able to comply with the latest safety. The chances of being able to retrofit into a standard system and maintain this type of security are very unlikely. So what we will generally say is cut it off at the plinth. We'll supply you a new panel. It'll be fully certified. But yeah, absolutely, the older regulations we do not need to comply with this. And in low voltage, that's going to become a big thing, I think, in our industry. When as they come into low voltage equipment, none, like I don't know what the percentage is, but I'm going to say 85% of low voltage systems offshore are not ARC contained. And when that does become a requirement, we're going to have a lot of work to do to retrofit. So what we do is we take these panels to a shop and we put these shorts on, and we pump in all of the fault current that we could ever see, and we do that through hard shorts. We do it through flash wire to be able to create an electrical arc. We do a number of different ways, and we contain the panel with targets, paper targets on the outside. Very simple. If the paper targets remain at the end of the test, you've passed. If they don't, you failed, and we go again, and we have to change the design and go again. So that is the way that we've got to pass. So that covers, of course, heat as well as shrapnel coming out. So heat's another important one. Depending on how fast you can clear the fault, you have this enormous pressure that just goes out, and you have all of the shrapnel. But depending on how long your protection system, and sometimes it could be up to a second that it's running, you have this enormous heat that that generally starts a fire. So how thick are the walls and all of your metalwork, etc., to be able to contain that fire and stop a fire from spreading, again, is an important part of the test. So we need to be able to, our longest ever protection system that we will put on board, will the panel be able to contain a fire? So I just get a standard example, which I could talk through of some of the things that we do. So this system here is our AC drilling system, so thought relevant to this industry. This is the control, and this is an inverter system that will control all of the mud pump, the drawworks, top drive motors, etc. on board a vessel. And it's common DC link, and it is the highest level of power of fault current you will get on these vessels, because it feeds in from all the generation switchboards, and it has one common DC link which feeds multiple different load feeds. So we have all of these regenerating energy sources in the motors coming through onto this DC link. We have an enormous amount of capacitors, and we have the largest amount. We have feed in from every single generation switchboard into this board. So. Yep.
Is the DC link, is it supplied from both sides?
Mm-hmm.
So
it is.
In isolation,
yeah.
What safeguards are there for that equipment?
So each system here, so I'll give you an example. Here we have these two sections here are the diode front end in this case, rectifier feeds. They'll be fed from two sides of the board. In between them, there is a manual DC isolator. So what we would recommend in most practices is for that DC isolator to remain open and only ever close when so we need to be able to maintain drilling operations if you lose half the board as the bottom line. So we need, if you lose half of your generation capability, we want somebody to go and switch that DC, connect it to the other generators, and be able to carry on as normal. So, but generally, that in 99% of cases, that is an offload system that will require you to shut down that side of the bus, close it. Right, so the idea of all of these future designs that we're doing is nobody can open a door, nobody can switch any switch anywhere close to the panel. And that's all of the design aspects that we've tried to encompass here. So I'll show you some of the ways that we've tried to do that. So one of the major things is, again, this battle for footprint, to be able to get the smallest and lightest boards out there. presents this challenge, and that what you end up doing is putting all of your controllers, all of your indication, all of your instrumentation in the same place that you have this enormous amount of power. And so that's a real focus for us to try to stop that happening. So what we do is we have main power sections that you have no access to. So these incomers, you can't get into them. You cannot get into them without shutting it all down or using a key system and getting in. From there on, all of these sections, these are individual drives. You have a door within a door. So how can we get all of the things that you might ever need to see as a maintenance crew or perform any testing? How can we get them outside the area where you're going to see, this board could be rated at 125 KA. So it's enormous fault level. So how can we ensure that that person will never go in and open that door when energized? So we lock the main power doors and we bring out the control, we bring out all of our instrumentation, we bring out everything to terminals you might ever want to meter, all out into this little control doors in front of the main doors. And that allows then electricians, everybody to go in there without opening those main doors. However, that's a step forward, but you're still crossing over a barrier. You're still coming within a barrier of a fault level so you still need to be in full 40 cal suits and above and etc. This is not, if you're standing right in front of that door with that opening, then we have proven that at that fault level, you will be okay. However, that is when it left the factory with all bolts in place, no modifications to the doors. There's all kinds of implications that could happen that would prevent your safety. So it has to be married with an onboard safety of work practice to say, you will not go into that room without the full PPE and only in extenuating circumstances and etc. And how can we also reduce the fault level before you go into that space? So the thing that I was going to really try to get across was the balance that a manufacturer's got to go against being shipyards being able to want to place orders with us and getting the highest level of safety. Because there's nothing going to say that we need to put input sharing reactors as an example. We'll put input sharing reactors into a drive system, and what that will do is limit the fault current. So it's a great system that will reduce the risk on the DC, but there's no regulation in the world that will say that you need to do that because it's on a case-by-case basis. And if we go up against another competitor, then we are going to be slightly more expensive because we've done that. We are going to probably be slightly bigger and slightly heavier. So this is the balance. It's not, if the final operator was buying this equipment, then it would probably be a different story because you could explain that and that would be understood. But the nature of our business is shipyards procure equipment, and shipyards are looking to meet their spec, which is the cheapest, et cetera, et cetera. So it's a real balance we've got to come. So I think there's a lot more that manufacturers could do to reduce this capability, to reduce this possibility, but difficult to do it and remain competitive. So one other concept here is the idea of fault-free. So this is all based on the fact that somebody's went in and dropped a spanner or a wrench across the bus bars, or something's become dislodged. There's one other serious concept which again isn't regulated but should be, which is how can you just prevent any exposed terminals being available in the first place for that to happen? So can you insulate all of the bars? Can you ensure that every single live terminal is covered? And they aren't in general, but that's a great way of doing it. So where we have our highest fault level, so when you come into that section, as an example, that first section, before we go through these input sharing reactors, we have the highest fault level of the system. So when we do that design, we will ensure that no matter what you do, no matter what comes unlodged, no matter what a personnel accidentally puts in there, they cannot cause a short circuit, and that's the best cause of defense. So and here's an example of that. So just fully insulating the systems completely, and only bringing the copper out exposed when we need to do a cable connections, and even then we should really be using a boot system or whatever onto these cable connections. So again, nothing, you could throw something in there, nothing's going to happen.
system?
Yeah, so one of the problems is you have most of these tinned copper bus bars that connect, and at some point you're going to bring a cable onto that. So you can cover that these copper bus bars with insulation. But what do you do when you need to when the shipyard or anybody needs to be able to come in and put that cable on, and also take that cable off to be able to do insulation testing? So the best way is generally to use a boot system where you take a high insulation structure and you put it over the cable, and you literally cable the cable, and then you bring it back over. That's a boot system. So keyed interlocks is not a requirement in low voltage equipment today. So we would do it as standard, but again, the example was given before of you're working on a piece of equipment, and then again take that multiple drive systems. You're working on a mud pump, you turn around, and you've suddenly opened the top drive cubicle. It looks exactly the same. How do you prevent that? And one of them is, the only real way in my view, is by keyed interlock systems. So you have a key in your hand, you physically cannot open that door until. But again, adds costs and potential reliability issues. These systems, another system on that system is a system that can break, can fail, and can cause downtime. So it's not seen as a positive. Other things is cooling. So we have these obviously in power electronics we have the need to cool all of this equipment. The high-speed IGBTs or whatever is firing the device need to be cooled, and we generally do that now with liquids, and we pump that through. One of the challenges is that to be able to expel all of the heat that is produced in these panels, you need to force a lot of air through it as well. So there's one thing, liquid cool, but you need to force air, and where you need to force air through it, you need an opening. You need to be able to draw that air through, and that's again proves to be a technical challenge in terms of ingesting dust and in terms of weak point during arc. So one of the solutions to that is going to an entirely water-cooled system with an internal heat exchanger, where you literally seal off these units. And so it's what we would do for when we supply solar inverters in the middle of a desert. We would supply this cabinet. It would be completely bomb-proof, no outside opening whatsoever, but we would have to add a lot of cost and material to be able to do all of the internal cooling and have no forced air. So it's another potential solution. But then there's the general design benefits. You need to take where you could never regulate for it. You just need to use strong manufacturing companies to do it. You know, how do you ensure that you joint your copper in a certain place that which will be your weak point in all of your copper places? How can you do that in the area where you're going to have the least fault level, etc.? How can you ensure where you're jointing cooling pipes is not within anywhere that could fall off, a bolt could fall off, etc., and fall onto an exposed terminal? So a bunch of different manufacturing practices like that. So overall, that's pretty much all I've got. It's just the balance that we have in manufacturing. We have to manufacture these products, we have a lot of different techniques we can employ, but being able to do that in a really cost-competitive way is the challenge that we have. But the answer is there is no one answer. There's no answer to saying protection systems are going to do it. There's no one answer to saying optical arc flash is going to do it, or even arc containment is going to do it. It has got to be a mix of them all, especially in the offshore environment, which is pretty unique when we run our own generation and all of this enormous loads on board. So I think that's all I've got.